We all just expect it, don't we? A perfect, unbreakable connection to the world. But behind that illusion of being always on, there's this fascinating dance of technology designed to catch things the moment they fail. In this explainer, we're going to pull back the curtain on the magic that keeps you online, even when a critical piece of your network just vanishes. Come on, we've all been there, right? You're right in the middle of a video call, maybe a game, just browsing, and then poof, nothing, total silence. Your connection is just gone, and you might think the whole internet broke, but nope. More often than not, the problem is way, way closer to home. So what's the culprit? Well, it's almost always this thing called a single point of failure. Think about it. Your laptop, your phone, every single device on your network is told to use one and only one door to get to the internet. That door, that's your default gateway. And if it suddenly slams shut, your entire network is instantly cut off. Trapped. So here's our game plan for figuring this out. First, we're going to pinpoint that vanishing connection. Then we'll dive into the clever virtual illusion that networks use to trick our devices. We'll watch the seamless takeover happen, take a quick look at the different tools for the job, and then see how engineers actually control the whole process. And finally, it all boils down to this really big choice: resilience or performance. See, your computer is really built for simplicity. It trusts one and only one exit path. It has no clue that other routes might even exist. And it's that single-minded trust that makes the default gateway the absolute weakest link in the entire chain. When it goes down, everything behind it is stuck. I mean, think of it literally like the only door out of a room. All your data, every packet, is funneled right through it. So if that door suddenly locks, well, everything and everyone inside is stuck. That's the exact problem that smart network design is meant to solve. And the solution is pretty brilliant. So how do they solve this? Well, with something called a first-hop redundancy protocol, or FHRP for short. Instead of trying to build one router that's completely invincible, which is impossible, these protocols create this clever illusion for your devices. The illusion of a single virtual gateway that never, ever fails. And this is where it gets really cool, because it creates two totally different realities. From your computer's perspective, it just sees one thing: a single, stable gateway that's always there. But what's really happening on the network is way more complex. Behind that one virtual identity, you've got multiple physical routers all working together, ready to jump in at a moment's notice. Okay, so this is the heart of the whole concept. The network creates this virtual router. It gets its own IP address and its own MAC address, just like a real one. One of the physical routers in the group gets elected as active. It's the one actually doing the work, moving your traffic. The others? They're in standby, just quietly monitoring, listening, and waiting for their cue. Right, but how does this takeover actually work? When the active router fails, maybe it crashes, maybe someone unplugs a cable, how does the standby router know it's time to step up? And how is that switch so fast that we never even see a glitch? It all boils down to this simple three-step dance. First, the active router is constantly sending out a little hello packet. It's like a heartbeat, telling the other routers, I'm still here, I'm okay. When that active router fails, the heartbeat just stops. The standby router, which has been listening the whole time, notices the silence, and boom, it instantly takes ownership of that shared virtual IP and MAC address and becomes the new active router. The best way to picture this is like a relay race. The physical routers are the runners, and the baton they pass between them, that's the virtual IP and MAC address. And because the baton itself never changes, the race just keeps going, completely seamlessly, for everyone watching. In this case, for your computer. And that, right there, is the whole point. It's the magic trick. Your computer was sending data to that virtual address before the failure, and it's sending data to the exact same virtual address after the failure. It has absolutely no idea that a whole physical device swap just happened in the background. The connection just works. Now, of course, like with anything in tech, there isn't just one tool for this job. Engineers can pick from several different first-hop redundancy protocols, and each one has its own little quirks and features. The right choice really depends on the gear you have and what you're trying to accomplish. So let's meet the big players here. HSRP is Cisco's baby. It's super powerful, but it kind of locks you into their gear. If you're mixing and matching different brands, you'll want the open standard, VRRP, which does pretty much the same thing. Then you've got GLBP, and this one adds a really cool twist. Instead of one router sitting on the bench, it can use multiple active gateways at once for both failover and balancing the traffic load. We'll come back to that one. And IRDP. That's a much older one you probably won't run into.
Okay, to really get how this works under the hood, let's zoom in on HSRP for a minute. See, network engineers need to have precise control over which router becomes active and when. You can't just leave it up to chance. And they use two key settings to manage this: priority and preemption.
When a bunch of HSRP routers first turn on, they basically hold an election to decide who gets to be the boss. And the winner is decided by a simple number, its priority value. By default, every router starts with a priority of 100. So how do you make sure your main, most powerful router always wins that election? Easy. You just give it a higher number, like 110. The router with the highest priority wins, period. It becomes the active gateway. Simple as that. But wait, there's a catch. Priority decides who wins the first election. What happens if your main router fails? The backup takes over, and then the main router comes back online. Well, without another setting, called preemption, it'll just sit there politely. Preemption is the key. It's what gives that higher priority router permission to say, "Excuse me, I'm back," and reclaim its active role. So priority picks the boss, but preemption lets the boss take back their chair. And the speed of this whole failover is all about timing. The active router sends out that hello heartbeat every 3 seconds. The standby router waits for a hold time of 10 seconds. If those 10 seconds go by without hearing a peep, it assumes the active router is down and immediately takes over. So we've seen how networks build in this incredible safety net, this resilience that's all happening invisibly to keep us connected. But this brings us to one last really strategic choice every network designer has to make. But before we get to that choice, let's just lock in what we've learned. The problem? A single gateway is a huge point of failure. The solution? That elegant illusion of a virtual router. The mechanism? A constant heartbeat that triggers a seamless takeover when it stops. And the controls? Engineers use things like priority and preemption to stay in charge of the whole process. When you really think about it, all of this, the elections, the heartbeats, the silent takeovers, it's this incredibly complex dance happening in the background all the time. And it's all engineered for one single purpose: to be completely invisible, so your connection just works. And that quote right there really nails it. It shifts the whole conversation. The goal isn't just about surviving a failure anymore. It's about actively optimizing the entire network's performance. And this brings us back to that protocol we mentioned earlier, GLBP. Is it really enough to have an expensive, powerful backup router just sitting there, doing nothing, just waiting for something bad to happen? Or should we be asking more from our networks? And this leaves us with a big question. When you're designing a network, the choice isn't just about preventing downtime. It's about performance. So how do you choose? Do you go with a protocol like HSRP for simple, rock-solid failover, even if it means leaving a powerful piece of equipment on standby? Or do you pick something like GLBP to not only survive failure, but to also share the load and squeeze every last drop of performance out of your gear every second of the day? It's that fundamental choice between pure resilience and active efficiency.